Assalamu alaikum students, how are you? We have started our subject of classical mechanics and we have discussed about the Newtonian mechanics and starting with the macroscopic properties of the objects and the motion of the objects, and with reference to that we have discussed about the frame of references involved in the motion of the objects. As we know that the motions are relative to each other. So now for according to the Newtonian mechanics, as we have discussed before that motion of the object is very important, and according to the motion there are three kinds of laws for the motion, and that is under the Newtonian mechanics, which was described by Newton first law, second law and third law. And you know that Newton's first law is regarded as the object is tend to behave or keep the state as it is, as if it is of motion or as it is in rest. And for the second law we know that force is equal to ma, means that the body will accelerate as the force is applied, uh, and acceleration is inversely proportional to mass, means that if the mass is of greater mass will tend to move with small acceleration. And now, and for the third law of motion, that is stated as the action reaction forces are equal and opposite to each other. Then we have discussed about the torque and angular momentum, and angular momentum and torque are related to each other. Then we discussed about the conservation of linear and angular momentum, and then we discussed about the system of particles and motion of system of particles under the classical mechanics. Now we are going to discuss the further in the classical mechanics under Newtonian mechanics about the work energy principle or the conservation of energy. How are they related to each other? Now starting with that, in classical mechanics, we will state that, as in previous classes we have studied about the work energy principle. You know that it tells us about the amount of work done on the object or system will equal the change in kinetic energy of the object or the system. Follow along it in this worked example and understood how to calculate the net work on the object and solve the change in the velocity. Now moving further, starting with the work energy principle, we will state as, in today's lecture we will discuss about work energy principle and the conservation of energy. Then the rectilinear motion of the single particle without retarding force and with retarding force, and the motion of the particle under the retarding force, and further there is the explanation for it. At the last there are the references. Some of the examples regarding the work energy principle are, as we know that in physics the concept of work and energy is thoroughly correlated and linked to the force. It is because whenever force is applied to an object, there is some work done on it and also some change in the energy is produced. We can say that work is a physical activity that includes the movement in the direction of the applied force. That is stated as in the definition for the work energy principle and the conservation of energy. Now, to understand this, we can say that the increase in kinetic energy of a rigid body is caused by some amount of work done on the body due to the force acting on it. This is known as the work energy principle. Similarly, the decrease in the kinetic energy is brought about the negative work done by force acting on the body. There are some examples under the work energy principle and the conservation of energy. Number one, we can say that a car moving in with constant velocity is accelerated. Hence, there is an increase in velocity, so the kinetic energy is increased by the positive work done by the engine. A second example under this falls a ball dropped from a height. h. Work done by gravity increases the velocity of the ball and thus the kinetic energy increases before hitting the ground. Number 3, there is another example. Brakes are applied in a motorbike and it comes to rest after a few seconds. Here work done by the brake is negative, so with decrease in velocity the kinetic energy decreases. Here you can note that work is said to be accomplished by only if there is some displacement of the object. In the case of no displacement but the force is applied, then the work done is zero. However, energy does not depend on whether some displacement is or not. For example, a man pushing a wall is applying the force to move to a certain distance. The wall does not move and hence the work done comes out to be zero. These are the some examples under the work energy principle and for the conservation of energy. Now moving further, starting with our topic. Now for starting with our topic work energy principle and the conservation of energy, we know that the work done on we have considered a path of A to B, and that path followed is any random path that can be a curved path or a straight path. Now for the work done from the initial point A to B, from moving an object from the point A to B, the force acts on it and that work done is given by for the path WAB. This path is divided in small patches of this small infinitesimal small displacement d. The work done WAB is equal to integral of AB for the path AB f dot dr. As we know that the work done is equal to f dot ds, f dot d. For the small patches divided in for the path A to B, here the displacement is given as integral of AB dot integral of AB dr. So that is the equation 1. We know that S is equal to Vt here as there is the small patch displacement. So for the small displacement d, we have the displacement dr is equal to vdt, that is same as s is equal to um, S is equal to Vt. Now we know that force is equal to F is equal to ma, substituting the value for acceleration, that is we know that acceleration is equal to derivative we know that that is equal to rate of change of velocity. Here acceleration in small infinitesimal parts is divided by dv over dt. So putting these values in the above equation, we get that WAB is equal to integral A to B into m into dv over dt bracket close dot into putting the value for the dr, we get v dot dt, that and closing that bracket is equal to mass into as mass is constant, so we take out of the integral A to B. Then writing the equation for dv over dt uh, dot v. Now as we are taking the dot product, so we have to solve that part. We know that if we have v dot v and solving it by product rule, uh, taking the differential and applying the product rule, that comes out to be d by dt into v dot v, that will be equal to 1 that will be equal to 2 dv over dt dot v, comes wab is equal to m into 1 by 2 integral a to b uh, dv d over dt into v dot v. Now the work done and is equal to wab is equal to 1 by 2, and applying the limit, differentiating and applying the limit, the integral cancelling the integrals, we get that WAB is equal to 1 by 2 mv square, limit is a to b, applying the limit, then we get 1 over 2 mvb square minus 1 by 2 mva square. That comes out to be WAB is equal to TB minus TA. Here we are representing the kinetic energy with the symbol capital T. So here the work done shows that final work done minus initial work done, that is the change in the kinetic energy. WAB is equal to del T is equal to change in kinetic energy, which is the energy principle, work energy principle I stated before in the previous introduction. This is called the work energy principle. As I told before in some of the examples, that the work done can be positive or negative depending upon the state of the energy or the work done on the object. So if we say that TA or the initial work done is greater than the final work done TB, then here the work done AB will be less than 0. It means that work done is done by the particle against the force, and the kinetic energy has decreased. So that is shows that it will be the negative work done. Now if the initial work done is greater than is initial work done Ta, sorry, initial kinetic energy Ta is less than the final kinetic energy TB. Here we see that the work done AB will be greater than 0. So we see there here that the work done on the particle by the force, work done is done on the particle by the force, and the kinetic energy has increased. So this shows that will be the work positive work done. The regarding this, the previously examples I have told you about the work done can be positive or negative. These 2 points state the example for the work done. How can the work done be positive and how can work done by can be negative? For the negative work done, removes or dissipates energy from the system. There are two examples. In pulling a box of books along a rough floor at a constant velocity, as we have done the positive work on the box, that is, I have put the energy on the system. The force of friction opposes the displacement always and does the negative work done. And for the positive work done, when the force and displacement are in the same direction, the work performed on the object is said to be positive. Example, we can say that is of when a body moves on a horizontal surface, force and displacement are in the forward path, the work done is in the case is positive. The force is called conservative force if the work done is independent of the path followed between the initial and final points. We have discussed in the previous lecture that there are two kinds of forces, that is the conservative force and the non-conservative force, and we have discussed that the conservative force is that in which the work done along a closed path is 0, and non-conservative force is that in which the work done is not 0. And we have discussed another description for the conservative force. According to the work done in a closed path, we have written as closed integral f dot dr, that is equal to 0, that shows the conservative force, and in a closed path is 0. In a closed path means that from where the object started its motion, the object moves along a path that brings back to its the starting point. So the work done along a closed path is 0. And we have discussed about that in the previous by using the Stokes theorem, or you can say that curl of f del cross f, that is equal to 0. That also shows that the cross product or the for the force, that is equal to 0. The value of del operator is partial over partial x, partial over partial x I cap plus partial over partial y j cap plus partial over partial z k cap, and taking the cross product with the force component fx fy fx I cap plus fy j cap plus fk fzk cap, we get the result 0. We have discussed in the previous lecture. Now we know that the potential energy is related with the force, and we know that the negative gradient of the force of the potential energy, that is equal to force, which is written as F is equal to minus del V. As we have discussed for the potential gradient, F is equal to minus del V, we see the minus sign. That means that the force exerted by the force field always tends to lower the energy and will act to reduce the potential energy. The negative sign on the derivative shows that if the potential energy V, here we have been represented by V, increases with increasing R, the force will tend to move it toward a smaller R to decrease the potential energy. That is the relation for or the description for the negative sign here. As we know that F is the definition of the potential energy, is a source exerted by the force field in the such as the gravity, spring force, etc. The potential energy U is equal to the work you must do against the force to move an object from the U V is equal to 0, the reference point to the position R. The force must exert to move it must be equal to but oppositely directed, and that is the source of the negative sign here. Now for the negative gradient of the del minus del V, we write the negative gradient of V, that is equal to force. F is equal to minus dV over dr. Cross multiplicating the dr on the left hand side with F, we get F dot dr is equal to minus dV. Now integrating both sides, we get integral of AB F dot dr is equal to minus integral of AB dV. According to the equation 1 previously, integral a to b f dot dr is equal to the work done AB. So substituting the value work done WAB and integrating the differential dV, we get minus into VB, and applying the limits we get minus VB into minus bracket VB minus VA bracket close. Multiplying the minus sign inside, we get WAB is equal to minus is equal to VA minus VB. That is the equation 3. Now for the work done to be conserved for the energy, these two equations can be equalized. So for the kinetic energy, we have got the equation for the work done WAB, that is equal to TB minus TA, and for the work done AB, for the potential energy along the path AB, that is equal to VA minus VB. Now rearranging the equation, taking VB from the right hand side with the minus sign on the left side, that becomes positive, and taking that minus TA from the left hand side towards the right hand side, that becomes the positive TA. So the equation becomes TB plus VB is equal to VA plus TA. Now we can rearrange that equation so that the initial total energy should be equal to the final total energy. That means the sum of kinetic energy and potential energy for the starting point, and the kinetic energy, sum of kinetic energy and potential energy on the final point should be equal. So according to this definition, we can say that the total energy of the isolated system remains constant. It means that it is conserved over the time, and that means the energy can neither be destroyed, neither be created, neither be destroyed. Rather, it can be transformed from one form to another form. For instance, we can say that chemical energy is converted to kinetic energy when a stick of dynamite explodes. If one adds up all form of energy that were released in the explosion, such as kinetic energy and potential energy of the pieces, as well as heat and sound, one will get the exact decrease of chemical energy in the combustion of the dynamite. Classically, conservation of energy was distinct from the conservation of mass. However, that is, however, in special relativity showed the mass related to the energy and vice versa. That is equal to E is equal to mc square. Now, as we are discussing for the conservation of energy, so that equation becomes Ta plus Va is equal to Tb plus Vb. This is called the law of conservation of total energy. Here we can see that the total energy T plus V of the particle is conserved for a conservative force. For a system having a friction, the force is not conserved, but still total energy of the particle is conserved. If we consider the work done against the friction, then the potential energy del V is equal to change in kinetic energy plus F dot dr, that is the frictional force. where small f is the frictional force or change in the frictional force value. It means that the total kinetic energy is the sum of the energy distributed during the motion of under the action of force. According to the conservation of energy, we have an example for the conservation of energy. When we roll a toy car down a ramp and it hits a wall, the energy is transferred from the kinetic energy to the potential energy. That is, the whole energy is converted into the another form of energy. As I have told you before, that energy is changed from one form to the another, but it cannot be destroyed or not can be conserved, uh, created or destroyed. As we know that friction, air tension, and air resistance and tension in the cord are the examples of frictional forces. So, according to the definition, we can say the question arises: what is the non-conservative force? We can say that a non-conservative force is one for which the work depends on the path, and hence it is essential to know where the object starts and stops. Examples of non-conservative are the air resistance I told you before, friction and the tension in the cord. So, moving further, as we can say that the non-conservative force, as frictional force or the air resistance, is the force that incorporates a significant change in the mechanical energy that is associated with the mechanical work. This means that the work done by the non-conservative force adds or removes a part of mechanical energy in the form of kinetic or potential. It does not depend on the path followed by the moving particle, as I told you before. It does not obey the path, but it depends upon the initial and final velocity of the object from where the object started and where it will stop. The work done by a non-conservative force is irreversible in nature. It means that when the object changes its position, path is not regained again. Then the work done by a non-conservative force is not equal to zero. So that shows that the non-conservative force is not equal to zero. Now, starting with the topic rectilinear motion of a single particle without retarding force, we know that first we will discuss about the rectilinear motion. What is rectilinear motion? We say that the straight line motion of the particle moving in a force field, that is called a rectilinear motion, or we can say that a motion, linear motion in which the direction of the velocity remains constant and the path is a straight line is a rectilinear motion. Or we can say that one-dimensional motion along a straight line is a rectilinear motion. So we can therefore be described the mathematically using only one spatial dimension for the linear motion of the object. The linear motion can be of two types: uniform linear motion with constant velocity or zero acceleration, and a non-uniform linear motion with the variable velocity or the non-zero acceleration. Here we are going to discuss about the motion of a particle or a point like object along a line can be described by a position x which varies with the time. An example of the linear motion is an athlete running 100 meters along a straight track is also is the linear motion example. As we know that according to the Newton's first law, that the object that do not experience any net force will continue to move in a straight line with a constant velocity until they are subjected to a net force. In under the everyday circumstances, external forces such as gravity and friction can cause an object to change the direction of its motion so that its motion cannot be described as linear. Now, for the rectilinear motion of a particle without the retarding force, you know that retarding force is the dissipating force, but here the dissipating force is absent. A force F is said to be a field, to be field if be the force in the field if it depends on the position of the particle and not on its velocity or the time. If the rectilinear motion key takes along takes place along the y-axis, then the equation of motion reduces from x to y. So we can see there is a particle or the object O moving in on a straight line towards the vertical direction. So F is equal to MAY, that is equal to M dy dot over dt, and that force will be equal to Fy. Here Ay, that is the acceleration in y direction, that will be equal to dvy over dt, and vy is the velocity in y direction, so that will be equal to dy over dt, so that will be equal to y dot, where y dot is the velocity of the particle and Fy is the one-dimensional force field along the y direction. Now consider a particle is projected vertically upward with the speed v0 and moves in a vertical straight line under the uniform gravity with no air resistance. Here the retarding for the air friction is absent. Let the v velocity is acting up on the object in the upward direction in the time t, then the equation becomes m dv over dt is equal to minus mg, and that is the gravitational force mg. The two forces are equalized, so the equation becomes m dy over dt is equal to m dv over dt, ma f is equal to ma, and f is equal to minus mg is equalized, so m dv over dt is equal to minus mg, and cancelling m on both sides, that gives dv over dt is equal to minus g. Taking the dt on the left side, from the left side below to the right hand side in the multiply, that gives dv is equal to minus g dt. And now integrating for the path, that is integral v naught to v dv is equal to minus integral to 0 to t for the time g dt, and applying the limits we get integral v y mod vy limit v naught to v is equal to minus gt limit 0 to t. Applying the limits we get v minus v naught is equal to minus g into t minus 0. That gives the final relation for v minus v naught is equal to minus gt, and taking v naught from the left hand side to the right hand side, we get v is equal to v naught minus gt, that is the equation 1. That is similar to the equation vf is equal to vi plus at, which is the equation of motion, first equation of motion. Here Vf is replaced by V, and Vi, the initial velocity, is replaced by V naught, and the acceleration is replaced by minus G, as the object is vertically moving upward opposite to the gravitational force. In linear motion, the directions of all the vector describing the systems are equal and constant, which means the object moves along the same axis and do not change the direction. So here we can see that object is moving along vertical direction. Now to find the upward displacement y in the y direction, as the object is moving vertically upward at time t, we can write the velocity v as v is equal to dy over dt, that is got from the equation s is equal to vt. Here s is dy and d will be replaced by dt, so v is equal to dy over dt, and equalizing the previous equation or substituting the value, we get dy over dt is equal to v naught minus gt. Taking the dt from the left hand side to the right hand side, we get dy is equal to bracket v naught minus gt bracket dt, and then integrating the equation with and applying the limits, we get integral 0 to y dy is equal to integral 0 to t bracket d v naught minus gt bracket close dt. Applying the integral and applying the limit, we get mod of y limit 0 to y is equal to v naught t minus 1 by 2 gt square, and applying the limit from 0 to t, we get y is equal to v naught t minus 1 over 2 gt square. Substituting or giving this equation number 2. That is that equation, you can see that is like the second equation of motion, that is s is equal to vit minus 1 over 2 gt square, 1 over 2 minus gt square. Here s displacement is replaced by the y displacement in the vertical direction, and the initial velocity here is not vi represented by but v naught. So that equation, and here is the minus sign for the object moving vertically upward in the opposite direction of the gravitational force. So equation is y is equal to v naught t minus 1 over 2 gt square. We have got two equations, the equation number 1 and the equation number 2. Hopefully you have understood the two steps for the two equations here with clearly. If there is any difficulty, you can work out with the uh, work according to that equation on your notes or register by solving it on it and understanding it. Now to find the maximum height, y maximum, we know that when the object reaches at a certain height, maximum height, there is a point where the velocity changes as the direction of the object changes. So when v is equal to 0 at a certain maximum point, putting in equation 1, t is equal to v naught over g. The above equation is, when v is equal to 0, from previous equation we get the value t is equal to v naught over g. We are left with the value uh, v naught uh, over g. So substituting this value of t in previous equation 2, we get y maximum is equal to v naught into v naught over g minus 1 over 2 g into v naught over g in whole square is and solving that equation, taking making this the equation as y maximum is equal to v naught square over g minus 1 over 2 g into v naught square over g square, cancelling 1 g on the second term, we are left with the v square g minus 1 over 2 v naught square over g, and taking v naught square over g common, we are left with 1 minus 1 over 2, and that gives the value solving 2 minus 1 over 2, and that is 1 by 2. So 1 by 2 v naught square over g is left, so we get v naught square over 2g. Now that is the maximum displacement covered by the object in the vertical direction. When the particle returns to the ground, it means that the total displacement covered by the object is 0. So when y is equal to 0, the equation 2 becomes, from the previous equation, 0 is equal to v naught t minus 1 by 2 gt square. So from here, taking the common t, we get 0 is equal to t into v naught minus 1 by 2 gt. Hopefully you are understanding till here. as when the object covers the displacement and hits the ground, the total time covered by t is equal to 0. So we are left with the equation 0 is equal to v naught minus 1 by 2 gt. So from here we get v naught is equal to 1 by 2 gt, 1 by 2 v naught is equal to 1 by 2 gt. So from here time will be equal to t 2 v naught y over g. It means that we see that when the object travels the vertical direction from ground to upward, that is v naught by g, and when it comes from height to the ground, that is also 2 v naught over g. So the total time covered by the object from the start to the end, that is t is equal to 2 v naught y over g. Thus, the particle returns after at the time 2v naught over g. So, it means that the object has covered the double the time covered by the object is covered by the object. So that is double the time. So 2v naught over g. Now here we are considering when the particle is moving under the retarding force or the frictional force. So the equation of uniform motion for a particle of mass m moving under the force F, we know that F is equal to dp over dt, and for substituting the value for p, that is equal to mv. So F is equal to d by dt into mv. F needs not to be constant, so that means, for example, a particle falling under the gravitational force Fg, and there is also a retarding force of air resistance Fr. So that equation will become that the total force will be equal to the gravitational force and the retarding force Fr. So we know that Fg is equal to mg, and retarding force will be equal to Fr v, that, and giving that equation number 1. And what is the retarding force and what is its effect on the particle. The whole dynamics will be in the vertical direction. So we consider that the particle is falling under the um, initial velocity v naught from a height h in a constant direction gravitational fields. We consider the equation in y direction. So we have a system that the vertical direct displacement is y, and the object is facing to fall towards the gravitational force, and the resistive force is acting opposite to the fall of the object, or the opposite to the gravitational force, that is the resistive force. So, gravitational force in the negative z direction is in the negative z direction, and the object is moving in the negative z direction here. So, the retarding force in the positive z direction. So there is we have written that the total uh, force is equal to mg plus frv, and given that equation number 1. Here r is the function of speed and or the drag force, a resistive force. So Fr is proportional to minus V, and here Fr is equal to minus mkV, where V is vector is equal to V magnitude into V unit vector, and we know that V unit vector is equal to V vector over V magnitude. So we can write Fr is equal to minus K V magnitude into unit vector. Substituting the value of V unit vector, we get here is a uh, exponential for the velocity minus in the form of minus a. So Fy is equal to minus mk a V unit V vector over V magnitude, where k is a positive constant. So equation k1 becomes F is equal to mg minus mk va V vector over V, and F is equal to mg minus mk V power a minus V into V vector. So here for the drag force, the constant used for the drag force velocity, that is in the form of k. Now we can say that for the velocity is less than 24 meter per second and nearly equal to 1 for higher velocities, but below speed of sound 332 meter per second, the drag force is approximately proportional to the square of the velocity. To solve that problem, we used a Stokes law of the resistance rather than the Newton's law. So here is a particle moving under the retarding force, which is Fr is equal to minus mkv in the horizontal direction on the right hand side. As we are dealing with the retarding force or the drag force or the air resistance as the object is falling from the height, so the fluid, so here the air layers are working as the fluid. So here the Stokes law of resistance is used rather than the Newton's law. So we can state that the Stokes law, a mathematical expression to that is the drag force is resisting the fall of the small spherical particles through a fluid medium, and that was given by Stokes. Here, the force is acting on a particular particle as it sinks through a liquid column under the influence of the gravity. So, the drag force acting upward in the resistance to the fall in the equal to 6 pi r eta v, in which r is the radius of the sphere of the object and eta is the viscosity of the liquid or the air resistance air layers, and v is the velocity of the object falling. So for that case, at a constant velocity of the fall, called the terminal velocity, the upward and the downward forces are balanced. So that is called the Stokes law of resistance here. Newton's law is not applicable as the resistive forces are present here. So the Stokes law is used in this place. So for the simple definition, we can say that according to that picture, the force that retards a sphere moving through a viscous fluid is directly proportional to the velocity and the radius of the sphere and the viscosity of the fluid, and that is 6 pi eta rv is equal to F. That is the retarding force applied on the object here. Now here we are considering a particle of mass and moving along x-axis under the retarding force proportional to the velocity Fv is equal to minus nkv. The only force acting on the particle is the resistive force according to the figure. So F net is equal to F is equal to minus mkv, and F net will be equal to F is equal to ma, so ma is equal to minus mkv. From here cancelling m on both sides, you get a is equal to minus kv. We know that acceleration is equal to dv over dt, so substituting that value we get dv over dt is equal to minus kv, and integrating that equation and applying the limits of v naught to v, we get integral v naught v dv over v. Rearranging equation is equal to minus k integral 0 to t dt. We know that 1 over v dv will be equal with the integral gives a natural log of v and limit v naught to v and minus kt 0 to t limit, and applying the limits we get log v minus log v naught minus k into t minus 0, and we know that the minus sign between the two natural logs can be written in the combined form as the uh, the real form, that is log v over v naught is equal to minus kt, and taking the log of inverse on both sides we get v over v naught is equal to e minus exponential minus kt, that is the value, and that gives v is equal to v naught exponential minus kt. Here we can see that the velocity final is equal to initial velocity into the exponential form. It means that the turning force during the retarding force being applicable on the object falls or changes the velocity exponentially with the factor exponential minus kt. Solving that equation, this gives equation the velocity of the particle moving under the retarding force depending upon the velocity. So we get v is equal to v naught exponential minus kt, and we know that velocity is equal to dx over dt. So substituting that value, we get dx over dt is equal to v naught exponential minus kt. Rearranging that equation, we get dx is equal to v naught into exponential minus kt. Integrating that equation and applying the limits for displacement, limit is 0 to x and for time 0 to t. So integral 0 to x dx is equal to v naught integral 0 to t exponential minus kt dt. So x or limit 0 to x is equal to v naught into exponential minus kt over minus k. Integrating that exponential, we get x minus k in the denominator, and limit is 0 to t. Applying that limit, we get x is equal to v naught minus v naught over k into exponential minus kt minus 1, as exponential of 0 is equal to 1, and that displacement is equal to multiplying the minus sign inside, we get x is equal to v naught over k into 1 minus exponential minus kt. That is the displacement covered by the object moving in the retarding for under the retarding force. This equation gives the displacement covered by the particle under the retarding force depending on the velocity. The daily life is the very good example for the particles or the objects moving under the retarding force, and the equations found out by that method here for the particle, for the velocity and the acceleration or the displacement covered by the objects is applicable to the daily life objects when the retarding force is present. There are a number of daily life examples where the real life application of retardation can be observed. A few of them are as below. Number one, when the object, as we discussed here, is throwing an object. When an object such as a ball or a stone or any other substance is thrown up in the air, it tends to travel the straight line. It reaches a particular point in the air, as we discussed here in the previous example. After reaching the peak point, the object begins to return back to the ground. The change in the value of the velocity builds when the object travels in the upward direction and tends to reduce gradually when the object returns back to the ground. This reduction in the value of the velocity with respect to time is nothing but the retardation. Number two is the example when the applying brakes to the vehicle. The application of retardation phenomena in real life can be observed by pulling the brakes of the vehicle to stop its motion. When the brakes of a vehicle are applied, the velocity with which the vehicle moves begins to decrease at a particular rate. This corresponds this corresponds to a negative rate of change in velocity that is typically known as the retardation of vehicle. There is another example, turning off the fan. When the switch of the moving fan is turned off, the rate of movement of the fan blades begin to reduce gradually. This rate of reduction of the velocity observed at a result is lower than the initial rate of change in velocity of the fan blades and is known as the retardation. One more example for the retardation is at the last is slowing down the swing. When a swing is not supplied with an appropriate amount of mechanical force, it tends to lose energy and slows down. Here, the rate at which the swing moves is known as the acceleration value, while the rate of velocity at which it tends to slow down is called the retardation of the swing. This is the topic here completed. Here are the references given from which you can follow. If there is any kind of difficulty, you can ask me. Uh, the book have to follow is most probable is the Goldstein. Other books are also helpful for you. Uh, thank you. If there is any kind of difficulty, you can ask me. Thank you.